Authored by veteran chemistry teacher Abdul Shakur, these two textbooks provide all the essentials that would not only enable students to master grade 11 chemistry, but to excel at the next higher level in this subject. What make these texts unique are their creativity and profundity with which concepts are explained for clarity and mastery. The following is one of a set of 44 different tutorials created by the author, using materials primarily from the text Chemistry 11 in Focus. I hope you enjoyed this video. If you liked it, please give it a thumbs up and don't forget to subscribe. We will see you in the next video and thank you for watching.
Today, our first lesson begins with atomic theories and atomic structure, and it is taken from page 8 to 11 from the textbook Chemistry 11 in Focus. What is matter made up of? How could one describe something one couldn't see? These were the questions that have perplexed and intrigued the human mind for thousands of years. The various endeavors to decipher the composition of matter and to bring to light its current description indeed represent some of the greatest of human achievements. It all began with some of the greatest human minds formulating theories about the composition of matter. What is a theory? The word theory has a Greek origin meaning to look at. People have put forward many wordings for the definition of a theory, but the one that I like most is the one that says, it is a well thought out statement that is intended to explain how or why an event, behavior, or phenomenon occurs. A scientific theory is based on evidence that is obtained consistently from scientific investigations. However, if any new, more reliable information emerges that relates to a current theory and does not support it, then a theory must be modified or rejected. Some of the earliest theories about the composition of matter were proposed by the following prominent Greek philosophers and were thus more philosophical in nature rather than scientific. Democritus. He theorized that if all matter is divided into smaller and smaller pieces, then there comes a point at which it could not be further divided. He called the smallest piece of any matter atomos, the Greek word for indivisible, Empedocles. He proposed the four elements theory that consists of fire, air, water, and earth. Aristotle. He opposed the theory proposed by Democritus. Instead, he adopted Empedocles' four elements theory, adding a fifth element of divinity that he called ether. Being brilliant and very influential, Aristotle's theory stood its ground for over 2,000 years until it was proven wrong by more scientifically sound theories. The most profound theory to be proposed next was by John Dalton. Dalton's atomic theory. In 1809, the English scientist and teacher John Dalton, nicknamed the father of modern science, used the atomic theory proposed by Democritus and his own observation of the solubilities of gases in water as a basis for his description of atoms and matter. Dalton's atomic theory is described as follows. 1. All matter is made up of very tiny particles called atoms, too small to be divided. As depicted here, we have a tiny piece of matter here with its atoms, and he's saying that an atom, thinnest element here, is too small to be divided into smaller pieces. Number 2, the atoms of all elements have identical properties in terms of size, mass, color, and density. Here we have a tiny piece of matter with all identical atoms. And here we have a different tiny piece of matter with all identical atoms. However, the atoms within this element are identical to each other. And the atoms within this element are identical to each other, but they're different from the atoms within this element. It's like me having a piece of gold here, all the atoms within gold are identical, and this being a piece of silver or lead here, all the atoms within this element will be identical, but the atoms of gold there will be different from the atoms of this piece of lead or silver here. Number 3, the atoms of one element cannot be changed into atoms of another element, nor can they be created or destroyed. In other words, if I have an atom of one element here, I can't change it to the atoms of another element here, nor can I create an atom, or I can't destroy this atom here. Okay? Of course, we know the alchemists tried unsuccessfully to change lead into gold by a process of transmutation. Number 4, atoms of different elements can combine in specific ratios to form compounds, or what Dalton called compound atoms. For example, in this case here, we're showing you how one atom of carbon is reacting with an atom of oxygen to form the compound carbon monoxide. In this other example here, an atom of carbon is reacting with 2 atoms of oxygen to form the compound carbon dioxide. See how I deliberately use separate atoms of oxygen here, because Dalton did not realize that certain elements exist as diatomic molecules such as oxygen, nitrogen, hydrogen, and the halogens. Thomsons Discovery of the Electron. Before the work of Thomson can be appreciated, the invention of a cathode ray tube must first be introduced. The cathode ray tube. In 1875, British chemist and physicist Sir William Crookes invented the first cathode ray tube. Essentially, it is created by placing 2 electrodes at the opposite ends of the gas tube, the inner walls of which were coated by a phosphorescent material, zinc sulfide. These electrodes were connected to a variable voltage source.
And finally, a vacuum pump was used to remove the air from the glass tube, which was then sealed.
So this is what it is. This is your glass tubing here. These are 2 electrodes. One is called a cathode, and the other is called an anode. And they are connected to a variable voltage source. And the inner walls of this tube here are coated with a phosphorescent material called zinc sulfide. And this here is your vacuum pump that is used to remove the air. And finally, this tube is sealed off here. Okay, let's look at Sir William Crookes' observations. At a certain voltage and at a very low pressure within the tube, a glow was observed at the anode end of the tube. Through further investigation, Sir William Crookes made some more observation. The glow on the anode side of the tube appeared to be caused by some type of rays that are coming off the cathode that he called cathode rays. How did he find out this? This is what he did. He placed a cross between the 2 electrodes and a screen behind the cross. Then he observed that a shadow of the cross was cast on the screen. When he did the opposite, by placing the cross there again, but then he put the screen on the opposite side of the cross, he did not get a shadow of the cross on the screen, and that made him believe that indeed the rays were coming from the cathode side onto the anode side. Not only that, Sir William Crookes used electrical plates and magnets to see how the rays were deflected by them. And he found out that the rays were deflected in ways which are identical to the ways in which negative charges were deflected. And that made him conclude that cathode rays were indeed negatively charged particles. So that was the work of Sir William Crookes, his invention of the cathode ray tube, and his discovery of cathode rays, and his conclusion that they are negatively charged. This brings us to the discovery of the electron by veteran scientist J.J. Thomson. Using a modified cathode ray tube, on April 30th, 1897, J.J. Thomson was able to show that the electron is a fundamental particle
of all atoms.
So the following figure here depicts his modified version of the cathode ray tube. Of course, this is a cathode ray tube. See, it's different from the one we saw from Sir William Crookes. So inside here now he placed an electrical heater, and in front of that heater there, just in front of it, is a circular metal disc that's made up of an element. Of course, this was made a cathode. And in front of the cathode were a series of cylindrical anodes that are connected to a voltage source. Running throughout the middle of these anodes were tiny holes. In front of these anodes here was found the deflecting system. The deflecting system consists of two sets of electrical plates. X plates that are arranged vertically, and the Y plates that are arranged horizontally. And then outside of that, you have a pair of magnets here that you use to create a magnetic field. This screen here is coated on the inside, again, with a phosphorescent material, zinc sulfide, such that any cathode ray that comes in this direction will be detected on the zinc sulfide screen as a bright glow. Okay, so let's see how this modified cathode ray tube works. This heater here, when the heater is turned on, it heats up the cathode and causes it to emit electrons. These anodes here in front of the cathode, because they are at a very high positive voltage, accelerate and attract the electrons in this direction. However, because of the tiny holes that are running through their centers, some of the electrons with their momentum bypass attraction by these positively charged anodes and impinge onto the screen here that creates a spot here. Now, what did Thomson do? Thomson used this spot here to monitor the effects of these electrical plates here and the magnetic field on the cathode rays that are coming in that direction. So let's see the findings of Thomson when he used the electrical plates. All right? With the Y plates on and everything is off, so here we're making that plate there positively charged and this one here negatively charged. What Thomson observed was this, that the spot here moved towards the positively charged plate, away from the negatively charged plate. So let's put this back here now and see what happens when you reverse the plates. When he made this one here negatively charged and this one here positively charged, again, he noticed that the spot here was always moving towards the positively charged plate away from the negatively charged plate. Okay? That means the cathode rays were moving like that. So the movement of the spot there is indicative of the way that the cathode rays were moving. So put that on back there now, at the center there. Let's see what will happen if you have this one on and that one off, this one on, that one off. What do you think will happen? It will move towards the positive plate. If you reverse the polarity on the plate, it will move towards the positive plate. So with these off now, with the X plate off, what happens when we have the
magnetic field
in north to south, this move in this direction like that. When you reverse the magnets, you change the direction of the field, it moves in the opposite direction. So based on his observation, Thomson was able to confirm Sir William Crookes' conclusion that cathode rays were indeed negatively charged. But one additional feat of Thomson was a calculation of the charge to mass ratio of the cathode ray. When Thomson trained the cathode using different metallic elements, and he calculated the charge to mass ratios of the cathode rays produced by these different elements, they were all identical. For example, when he used gold and he calculated the charge to mass ratio of the cathode rays produced, he got a certain value. The same value is obtained when copper, zinc, and other metallic elements were used. This led Thomson to conclude that the cathode rays are fundamental particles of all elements and that they are subatomic in nature. He renamed these cathode rays electrons.